So yeah, my name is Tingjun Yang. I'm going to present GPU accelerated machine learning inferences for offline reconstruction and analysis workflows in neutrino experiments. And this is the work I did with colleagues from Fermilab and MIT. So first introduction. So the machine learning applications, in particular, the deep neural networks, have becoming more and more popular in liquid argon TPC based neutrino experiments. The training of those deep neural nets has its own computing challenges. It takes usually from several hours to several days to train a network, but this is usually done only once a year, and we can also use the GPUs to do the training. The inference, on the other hand, happens on billions of events many times a year. So this is to apply the trained network to massive data sets of statistically independent events. And this poses a unique challenge across HEP because the inference can be slow on CPUs. A naive solution is to deploy GPUs on every worker node. So for example, we can equip each worker node with a GPU. But this model is not really scalable because the GPU can be costly. It's roughly between 20,000 to 30,000 US dollars per GPU. And also there are other related issues when we have so many GPUs in the computing farm. Another solution is to instead use the GPU as a service. So the idea is the worker nodes send inference requests and receive results from a machine equipped with a GPU. So the same GPU can serve a bunch of CPUs. And this can be done using the NVIDIA's free off-the-shelf Triton inference server. So at Fermilab, we developed this so-called SONiC framework, which stands for Services for Optimized Network Inference on coprocessors, including GPUs, FPGAs, and TPUs. So the idea is for this SONiC scheme is that the C++ code is running on the CPU to convert data format and send the inference request to Triton. And the DNN inference is handled completely by the Triton server on GPU. And here Triton stands for is an inference server from NVIDIA to use GPUs as a service. This project started with pioneering work done by LHC experimentalists with Microsoft Research to demonstrate a proof of concept for providing FPGA accelerated inference as a service for LHC experiments. And here you can find a published paper to summarize the early work. This scheme has been developed for CMS first, and now it's expanding to DUNE, Atlas, and astrophysics experiments. So the CMS Triton client is now officially integrated, and you can find more details in this GitHub webpage. Here are some details about the inference server. It's called AI Lab 01, which is located at Fermilab Furman Computing Center. And here is some detailed information about this server, and it has a T4 GPU, which is a lower power GPU for inference, and more powerful GPUs are available. And this work is just for demonstration. Recently, we submitted a paper to summarize the result to use GPU as a service for CMS, and you can find the paper on arXiv. We have also recently started applying GPU as a service to LAr TPC reconstruction using ProtoDUNE as an example. And we also submitted a paper to summarize the result using GPU as a service for ProtoDUNE reconstruction. And the paper has been just accepted for publication in the journal Frontiers in Big Data. And the goal is to use GPU as a service to accelerate ProtoDUNE reconstruction. ProtoDUNE single phase is a 1 kiloton LAr TPC experiment at CERN. This is one of the 2 prototypes for the DUNE far detector. And here you can see a picture of the neutrino platform at CERN. And this is the ProtoDUNE single phase cryostat. And we recently published a paper to summarize the first ProtoDUNE results. You can find it on arXiv. ProtoDUNE reconstruction uses a convolutional neural network to separate track activities from shower activities. Here is the architecture of the CNN, and here is the result of the so-called EM-track Michel ID module using this CNN. And here the goal is to tag the heats from the shower as red and the heats from track as blue. So this network has a roughly 12 million parameters, and the input is a 48 by 48 pixel patch, and each event has 55,000 patches. So there are lots of inferences per event. And this table summarizes the CPU time per event. And if you look at the middle row, which shows that the machine learning module, this EM-track Michel ID, takes about 220 seconds per event. This accounts for 2/3 of the total processing time per event. So it's a lot of time. And we're trying to speed this up using the GPU as a service. So the idea is the grid jobs are launched at the local Fermi grid at the Fermilab Computing Center. And this, so the non-machine learning modules are run on those local CPU farm. And once it comes to the processing of the GPU module, we send an inference request through this gRPC protocol, which was developed by Google, and send the request to the Google Cloud. And on the Google Cloud, we run this Triton server with 4 NVIDIA T4 GPUs, and the inferences are done by the GPUs, and the results are sent back to Fermilab computing farm.
We also you just over 2 minutes to go.
Okay, yeah. We also modified our reconstruction framework to allow to use GPU as a service. So the LAR salt is the common framework for LAR TPC reconstruction. And in this framework, this EM-track Michel ID uses this algorithm. And by default, this algorithm uses the TensorFlow library and the model to do the inference on CPU. And recently we added another inference interface to be able to use the Triton inference server on the Google Cloud to do the inference on the Google Cloud. So here is the result. So with the CPU, it takes 220 seconds per event to do this machine learning inference. And using this machine learning using the GPU as a service, this sonic approach, it's reduced to 12 seconds. So it's 18 times reduction in processing time for this machine learning module. And we also did more studies to understand the details of the processing time using sonic. I'll skip this part. So it takes about 12 seconds per event. And among those 12 seconds, 7 seconds is actually the pre-processing time on CPU. This is to prepare the image and also convert the data format. And 1.9 seconds is related to the bandwidth latency with a 2 Gbps network. 0.4 seconds is a travel latency to the Google Cloud platform in Iowa. And the real inference time on GPU is 2.7 seconds. Okay, I just have 2 slides. So we also did this data and time scaling model. So here we plotted the processing time as a function of a number of simultaneous jobs. And for the a small number of jobs, the processing time is a constant around 12 seconds per event. And up to 270 number of jobs, while the four GPUs starts to saturate, and the processing time starts to increase. And we determined the optimal ratio of the CPU processes to a single GPU is 68:1. And this ratio is determined by the CPU time for non-machine learning module and the sonic time for machine learning module. So in conclusion, sonic accelerates machine learning inference for ProtoDUNE reconstruction, and we see large improvement in the speed. And we are currently testing the ProtoDUNE offline production using GPU as a service on Google Cloud. So we are able to test this on large scale up to several thousands of jobs. And we will continue to optimize the GPU implementation with the TensorRT, with the tools such as quantization. We will try other hardware such as FPGAs, IPUs, and we will explore deployment at scale at the Furman Computing Center and the HPCs. Thank you, that's all.
Thank you, Tingjun. So do we have questions? Okay, there's one from Attila. Go ahead.
Yeah, so this looks very interesting, and it was very nice that you pointed out that it really takes a long time to run these inferences locally. I had no idea that it would take so long. But so I was just wondering that how much data do you transfer between Google Cloud, and how much data do you need to push there to run the inference, and how much data do you need to get back?
Yeah, I have a slide on that. So so the input is a 48 by 48 this 2D pixel image, and we have a roughly 55,000 inferences per event. So this adds up to about 4 gigabits. So that's the total amount of data. That's why for 2 Gbps bandwidth, it takes 2 seconds per event to transfer the data.
Wow. Okay. It's good that I asked. I had no idea that it would be this much. Okay. Okay.
Yeah, you know, the LAr TPC is really, it's a, you know, it has lots of information. So here is a picture of one ProtoDUNE event. This is only a small part of the detector. There's just say there's huge amount of information.
Okay. Yeah. Thanks.
Can I ask a related question, actually? I mean, is there, I guess, given in the context of that large transport problem, is there a way to pre-process in such a way that you compress the data more? And would that, would you expect that would introduce more delays between into the system versus what you're currently doing? So I guess part of the issue, you have a lot of.
Yeah. So yeah, this transfer time is something, you know, maybe compressing the image will help. And this is something we have not tried. But there's another, you know, we also started different batch sizes. So we can do the small batch, which means we have to send more requests per event. We can also do a big batch size, then we have to do fewer requests. And it turns out the big batch is preferred as it increases the inference speed and also reduces latency. Yeah, I think maybe it's related, but we can also explore whether compressing the image would help.
Yeah, okay, but I guess also in fairness, it's a small fraction of the remaining time.
Exactly.
Okay.
Something. I was really just wondering about what the economics of this are. I mean, obviously, well, it looks pretty clear that it makes a lot more sense than putting a GPU into every worker node. But would your sort of final deployment scenario be something like having a small GPU farm locally at Fermilab that you used a similar interface for? Because I would imagine if you use Google for everything, it probably the costs rack up quite fast.
Yeah, exactly. This work is just for demonstration. So yeah, eventually I think we will have to have a local GPU farm for the inferences.
Thanks. Yeah, makes sense.
Okay, great. I think that's time on the discussion, but thanks again. Very